Hello, everyone. So we are in this lecture going to talk about set theory. I'm basically breaking the lecture up into sub-videos so that each of you can take your time pacing through the material and you can take breaks in between. First, we'll talk about two main areas, and these are all in the notes, might I add. If you pull up those notes, you'll see that there's basic set theory, and then that there's the number systems and their cardinality. So these are two major sections we'll be talking about in our lecture. Now, in just terms of the first section, basic set theory, this video I'm going to talk a little bit about section 2.1, which is just the basic definition of sets, complements, universes, and the empty set. And so let's get right into it. So what is, just pull up my whiteboard here. Where did my whiteboard go? Okay. Now I don't know where my whiteboard went. There we go. So what is set theory? Put simply, set theory is a theory of collection. Now that might sound strange. Why do we need a theory of collection? The reason is simple. When we represent, a lot of things in math have to deal with this concept of a point. Think back all the way to basic geometry. What did you talk about there? What was the most fundamental unit that you can think of? Well, it was a point. Okay, so if you build on this idea of points, you'll notice, or at least one could show, that the idea of numbers are just nothing more than points in space. And the way we represent that is through a collection of points. So when we study the theory of collections, what we're in essence doing is studying math. So as it turns out, a lot of what we do, even in business analytics, in terms of the notation that we write, is almost entirely in set theory. And so if you don't understand the theory of sets, it's just hard to get through a lot of the textbooks that are out there out on the market. So to help guide you along, we're going to do a review of sets. So again, set theory is about the idea of this whole general notion of a collection. So the definition of a set is a collection of what we call well-defined objects. Okay, and the way that we usually represent sets in set theory is through capital letters. So for example, I might talk about the collection of, I don't know, all pillows I have in my house. I might represent that collection with the capital letter P, and I may say that this is equal to pillow 1, pillow 2, pillow 3. And suppose I only have 3 pillows in my class. The way in my house, the way that we write pillows or indicate a pillow is through the use of what we refer to as an element. So an element is nothing more than just a unique object I'm referring to. If I have 3 pillows in my house and I label them P1, P2, P3, then when I write this notation here, what I'm saying is that capital P is being used to refer to the collection, which is what I use with my horribly drawn braces here, the collection of distinct elements. And they need to be distinct. I can't have, this is something I can't have. I cannot have this. I cannot have something like P is equal to P1 and P1. That's not allowed in set theory. Why? Because these are not unique. If I have a set that is this, it's assumed that this is just the same thing as the set containing P1. So the first rule about defining sets is that we need to define them by elements. The second rule is that the elements need to be unique. The last rule is that elements can be defined as, and I'm going to use almost here, almost anything. I can talk about the set of trucks, the set of workers, the set of all people in the world, the set of all points in space, the set of all cups in a cabinet, the set of all students in a classroom, the set of all classrooms. Put differently, sets can contain other sets, right? So, for example, suppose I have two classrooms. I have classroom 1, which I'll denote by the set C1, and I have classroom 2. And in classroom 1, suppose I have Ahmed and Sue and Bob and Raphael. Suppose in classroom 2, I have, let's say, Joe, Ellen, Amy, and Jack. So I have two classrooms. I can then talk about the set of classrooms, C1 and C2. Notice that these are elements, but these elements, they are sets. So technically speaking, I have a set containing two sets, where the first set is Ahmed, Sue, Bob, and Raphael. And the second set is Joe, Ellen, Amy, and Jack. Okay, now notice this is not the same as the set Ahmed, Sue, Bob, Raphael, Joe, Ellen, Amy, and Jack. Why are they not the same? I will let you think a little bit about that, and we'll answer that in the next video. One small thing I would like to know is that there is one rule that we need to be careful of. And I'm going to go back here and write it as rule number 4, which is that sets cannot contain themselves. And believe it or not, this was a very big problem that a mathematician who invented a lot of this stuff by the name of Cantor ran into. And Cantor basically said that sets, sets can contain anything, maybe even including themselves. But then another gentleman by the name of Russell said, well, no, they can't. Sets cannot contain themselves. And here's one example. Suppose that we defined the set A to be the collection of any set R that is not in the set A. And so a question arises, is A in the set A? Well, think about it. If A is in the set A, then by definition, A is an element of A. And what needs to hold true about all elements of this set here? What needs to hold true is that for any set in this set, it can't be an A. But we just said that A, by definition, is an A. So therefore, it needs to not be an A. But how can an element be an A and not be an A at the same time? That's a big problem, obviously. So, a big rule of set theory, sets can't contain themselves. In the next video, I'm going to cover this idea of universes and complements. So I'll see you in the next video.